In this algebra video, we'll look at exponent etiquette, how you can expect exponents to behave in any situation. Let's start with a pre-quiz. How well would you do if this was a class quiz? Which of these rules, exponent rules, would you already get correct? Take a minute, maybe even pause the video, and see how many of these you can fill in on your own before we even begin. All right, now that you've taken a short few minutes here to check your own pre-knowledge, let's jump right in and see these different videos, or these different rules, how they interact with each other and why they are what they are. So to start with, rule 1. If you had an x squared and you multiplied that by the same base x, now cubed, if you expanded this, do you see that that first x squared, x times x, multiplied by that second x cubed, x, would give us a total of 2 plus 3 more, or 5 x's. 1, 2, 3, 4, 5. And if we expanded this x squared times x cubed, that's exactly how we could get the end result, and it would be x to the 2 plus 3, or x to the 5th. And that's why this first rule, a to the r times a to the s, where a is the same base in both of these, what you would do is you'd add those exponents. Now, some students are going to approach this by simply trying to memorize these rules. It's much better if you can understand them in a way like what you see visualized here to the right. Let's look at number 2 and see if you can visualize this. If we took our x squared and this time we raise it to the 3rd power, do you see what that would look like? Here's an x squared, a second x squared, and we need 3 of them, a third x squared. So we get 3 groups of 2, right? So 2 plus 2 plus 2, or it's repeated addition. So that's x to the 2 times 3, or x to the 6th power. When we have a base with an exponent and we raise it to another power, what we're going to do is multiply those 2 exponents. Rule 3, and how exponents could be expected to behave. If we had our x, and this time let's multiply it times a y, and let's raise that to the 3rd power. Do you see that that would be xy, 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 right? Xy cubed is xy times itself 3 times. Well, if I were to break this down to put the x's together and then the y's together, I could see there were 3 x's and 3 y's. So do you see that what I could do is I could write this as x cubed times y cubed. And I can see that it's visually more obvious when I expand that exponent. So rather than just staring at a rule that might or might not make sense at first, I've written out an example with a like base of x, and then in case 3 we have 2 different bases, base x and base y, and by working it out with a precise example, I can see that this is the same as this 3 distributing to the x and to the y. So I could write this as a to the r times b to the r. One more that will fit on this page, and maybe you already see the connection when you look at number 1. Do you see the connection? We had two like bases being multiplied, and what we did was we added the exponents. Here we have two like bases being divided. Let's see what we're going to do for that one. If I were to rewrite this as x cubed over x squared, and if I were to expand that, x times x over y times y, or I'm sorry, x times x, do you see that we could pair up two sets of x's that would divide out? Because x over x is just a fancy way of saying 1 times 1 times x. Look what's left standing after we reduce. We've got 1x. Do you see where that happened? We started out with 3 x's in the top, but then we subtracted the 2 x's from the bottom, the number of x's, if there were 2 of them, in the bottom, and that gives us the 3 minus 2, or x to the 1. When we translate that over to our rule, what you can see is that you subtract the number of x's in the denominator are subtracted from the number of x's in the numerator. So in other words, for the division of two like bases with exponents, we'd keep the same base and raise it to the difference, so subtract. The quotient connects to a subtraction problem or difference, and the product connects to addition. Let's continue with the next 4 rules. Do you see how number 5 connects so closely to number 3? For number 3, we had multiplication together raised to an exponent, and here we have a quotient raised to an exponent. And just like number 2, what we're going to do is, so if we take this a over b and raise it to an exponent, what we're going to do is distribute that exponent to the a and to the b. Let's look at that example, like an xy cubed. Can you see what that would look like? It'd be x over y times x over y times x over y. So we have 3 x over y's. And so I could rewrite that as x cubed over y cubed. And so in the same way, for our generalized rule, we could distribute that r to have a over b raised to the r power is a to the r over b to the r. Or when we raise a quotient to a power, we could break it up into the 2 pieces. This rule 6 is a little bit trickier because it comes up in many different ways. So you want to be really careful of how you're looking at number 6 and make sure you can visualize it from a few different ways. But when we have a negative exponent, what we're going to do is move that to the denominator, or if it's in the denominator, we move it up to the numerator. Here's an example. If I went back to this x cubed over x squared, what if I changed it to x squared over x cubed? Now, if I simply expand this, I'd have 2 x's in the numerator, 3 x's in the denominator, and I can see that the 2 subtract away. They divide out, so we're left with 1, but that 1x is left in the denominator. Now, if I applied rule number 4 to this, I'd get x to the 2 minus 3, which is x to the negative 1. And do you see that this x to the negative 1 has to be equivalent to this 1 over x? And what we do is we move this from the numerator, because you could picture this x to the negative 1 as being x to the negative 1 over negative 1. To make it positive, it has to move from the numerator down to the denominator. If we had, here's another example of this. If we had an x squared in the denominator, and I want to rewrite that, bringing the x squared to the numerator, I can do that by simply making that exponent negative. So this would be the same as x to the negative 2. But try that one a few ways, because here's another way you might see it. 3 over 5 to the negative 2. That's going to be, flip it, so 5 over 3 squared, because this 3 comes to the denominator, the 5 has to come to the numerator, so we just do a flip, and that's how we make it positive. But the way we'll write this is simply 1 over a to the r. But you could see it also as 1 over a, so it's the reciprocal of a to the r power. Last two examples, a to the 1 is the same thing as just a, and a to the 0 is actually going to be 1. Let me show you two examples that demonstrate this Rule 7 and Rule 8. If I have x cubed over x squared, and I applied the quotient rule, I'd have x to the 3 minus 2, or x. And you see that 3 minus 2 is x to the 1. But if I expand it, 3 x's in the numerator, 2 x's in the denominator, you see that that's just 1x. So we see x to the 3 minus 2, which is x to the 1, is equivalent to just x. So that's one way to visualize that Rule 7. And then for Rule 8, let me erase this 7 so we have a little space for it. This Rule 8, if I have x cubed divided by x cubed, that's just going to be 1, isn't it? Because we'd have 3 x's in the numerator, 3 x's in the denominator. They all divide out to be a 1 times 1 times 1. X over x is 1, x over x is 1, x over x is 1. So that's just a big 1. But if I did the subtraction, so if I applied Rule 4, the quotient rule, I'd have x to the 3 minus 3, which is 0, and do you see x to the 0 equals 1. It's one of the many things I just love about mathematics, that we don't have to memorize a bunch of exceptions. We can use one rule to discover other rules, and they bounce off of each other so nicely. So make sure you've practiced these. And here we go with the blank sheet again. How well could you fill in these blanks? Could you get all of them at this time? What if we rearranged them and put them in a different order? Or what if we changed them from A's to actual number bases or to other variable bases? Could you still get every one of those correct? Keep practicing until you can do it. But here's the completed sheet, and I certainly hope that this short video has helped you come a little bit closer to fully understanding how exponents could be expected to behave in various situations.